A random variable. That is something that can take any of the values that are in your sample space. It depends on chance. So rolling a dice, you have 6 random variables, 1, 2, 3, 4, 5, or 6. A discrete random variable is when you only have a possible choice from a list. So on rolling the dice, it's 1 to 6. Those are your only chances. It's not like, ooh, what am I going to get this time? 6-sided dice? 2.5. That can't happen, right? So we have only certain values from a list. It's discrete means that it's countable. Okay? If you throw a dice 4 times, how many 3s could you get? You could get no 3s. You could get 1 3. You could get 2 3s, 3 3s, 4 3s. Those would be the possibilities. A continuous random variable takes on any value so, for example, something that would be continuous. If I drop this dice on this square, it could land anywhere after that. And if I measure from this square how far away it is, it could take on any number. Because you're measuring it, it could be 2.5 centimeters. It could be 2.75 centimeters away. It could be 2.75381 centimeters away. Any value would be possible. Because in a measurement, you would have anything that could happen. Same thing, example here. Time it takes a car to finish a race. Cars don't finish in second intervals. It's not like they jump forward every second a certain amount. Right? Any time could be possible. A probability distribution, what we're going to be looking at for discrete random variables with a finite list of possibilities, is just a list and the probability of each one. Suppose you flip a coin twice. List the sample space for this experiment with a tree diagram. Not too hard. First time, you could get heads or tails, and then after that, you could get heads or tails, heads or tails. So our sample space is heads and heads, heads then tails, tails then heads, and tails then tails. That's our sample space. We could define one of the variables x as the number of heads that we did when we flipped the coin twice. And we can summarize this in something called a probability distribution. So for getting heads, how many heads could you get? Well, there's a possibility that you didn't get any heads. 0. There's a possibility that you got 1 head, and there's a possibility that you got 2 heads. So the key thing in a probability distribution, it's always going to look like this chart. You define x to be one of the discrete random variables. In this case, how many heads did you get? And what are your chances of getting, what's the probability of x equals 0? Well, we look at our tree diagram. How many of those branches have no heads? That's just this one. What's the probability on that one? 1 out of 4, because we could put 1/2 and 1/2, 1/2 and 1/2, 1/2. In fact, each of these branches would be 1 out of 4 in total for the probability. But when we go to our probability distribution, we've got 1 out of 4 here. What are the chances of getting 1 head? Did you see that there was 2 cases in our tree diagram? You could have got 1 head by getting heads first, then tails. Or you could have got one head by getting tails first and then heads. So the possibility of getting one head is 1/4 plus 1/4, which is 1/2. And the probability of getting two heads is 1/4. So the Px equals x is the probability that the number of heads is either 0, 1, or 2. One of the things that we always notice, if we sum this up, it equals to 1. Because the probability distribution chart lists all the possibilities you could get. If you flip a coin twice, you could get 0 heads, you could get 1 head, you could get 2 heads. There's no other possibilities. You can't get heads 1.5 times. You flip a coin twice, you're like, whoo, I got heads 5 times. You know, that doesn't make sense. So we list all the possibilities that could happen, and if we list all the possibilities and list their probabilities, well, that has to add up to 1 because you have 100% of the possibilities there. That's big idea number 1 in this unit. In a probability distribution chart, since you're listing all the possibilities, the probabilities have to equal 1. So this is the idea. Any probability of any of the items in there has to be between 0 and 1. You can't have a probability less than 0. You can't have a probability bigger than 1. If you sum, here's the sum signal, all those probabilities together, you will always get 1. So that's what that notation means there. So here's our tree diagram for tossing it 3 times. 8 possibilities. Now if you toss it 3 times, can you see that there would be 4 possible outcomes? If x is the number of heads that you got, you could have got 0 heads, 1 head, 2 heads, or 3 heads. How many of the 8 possibilities have no heads? Only 1. So the probability there would be 1 out of 8. I'll let you fill in the rest of the chart. I'll put the answers up in a bit. How did you do? Did you count the ones with 1 head to be 3 of them? So 3 out of 8. The ones with 2 heads to be 3 cases, 3 out of 8. And with all 3 being heads, only 1 case. Again, adding those up, the sum is equal to 1. A box contains 2 red marbles, 6 green marbles. 2 marbles are chosen at random with replacement. So what this means is you pull a marble out, look at its color, admire it, put it back in. They're like, ooh, I want to pull another one out. Look at its color, admire it, put it back in. We could draw a tree diagram. You pull out a marble to begin with. What could happen? It could be red or green. What's the probability of red? Well, 2 out of 8, green, 6 out of 8. Then you do it again. Again, you could get red or green, red or green. 2 out of 8, 6 out of 8, 2 out of 8, 6 out of 8. Probabilities stay the same because we put the marble back in. What's the word called again when the second time you do it is not affected by the first time? Close. Independent. If you didn't put the marble back, these would be dependent events because your probability would change on the second one. Since you put them back, these are called independent events. So our sample space, we could get red and red, red then green, green then red, and green then green. If we let X be the number of green marbles, you could get 0 green marbles, 1 green marble, or 2 green marbles. What's your chances of getting 0 green marbles? Can you see that that is your branch 2 out of 8 times 2 out of 8? If I multiply those together, I get 4 out of 64. Of course, you could reduce that. I'm going to just keep it out of 64 for now. One green marble, there's 2 cases. Okay, I'm just going to write the probabilities right here beside. Are you okay that this is 4 out of 64? 2 times 6 makes this 12 out of 64. This one 12 out of 64. And 6 times 6, 36 out of 64. So one green one, 12 out of 64 plus 12 out of 64 gives us 24 out of 64. And 2 green ones, 36 out of 64. Do they add up to 1? This is the best way to check if you've made a mental math error somewhere along the way. Yes, they add up to 1, so it appears that we've done everything correctly. I'd like you to try this one on your own. Well, yeah, I'll show you the lattice diagram in a second. You want to, would you agree if you rolled a 1 and a 1, your difference would be 0? 2 and a 1, your difference would be 1? All right, we'll do a check. How did you do? How many zeros are there? 6 out of the 36. How many 1s were there in the end? 10 out of 36. 8 2s. So this could be a totally different way to play a game. Because normally when you roll 2 dice, what do? You add them together. Monopoly. You roll 2 dice, you add them, that's how many you go. How would this affect your game in Monopoly if you subtracted instead? It would be really long to get around the board. You'd probably run out of money. Nothing like landing on Boardwalk and having to pay someone $2,000 and then rolling a 0 to stay in the same place and pay them again. Would there be different strategies? Right? My strategy in Monopoly is buy as much as I can around the first time around. I'd run out of money in this game because you'd almost hit everything. So maybe the strategy is not buy anything for the first little bit. But you're saying the game might be really, really long because it takes forever to get around the board. Now, I just want to try. Okay? We'll have to plan this out. Anybody not have a class, period 6? Bring Monopoly. We'll play the long way. See how it affects us. Do you still go to jail? Still get another turn if you roll doubles? Roll doubles, you stay in the same place. So if you have to pay rent again, and you get to go again. Whew. Could be interesting. Could be interesting. Is the following a valid probability distribution? Could this happen? Why not? Doesn't add up to 1. So this is not a realistic probability distribution. So now that you've got a sense for some probability distributions, we're going to take the next 10 minutes or so. There's 3 examples left in this section, and I want you to try each of those 3. We'll go over the answers. You can work with a partner if you like, or work on your own. If you want to check how you did on your first one, you could draw your probability distribution chart. They tell you probability of 0 is A, 1 is 2A, and 2 is 3A. So that's just a setup, taking the information from the question and putting it into your chart. What do you know about probability distribution charts? They always have to add up to 1. So A plus 2A plus 3A has to equal 1. You could solve for A. So you've got a situation where 2 things are happening. A tree diagram nicely shows what could happen. First, you could get white or red. Then if it's not replaced, now there's only 8 marbles left, and you could get white or red again. If X is the number of white marbles in your probability distribution, you could get 0 white marbles, 1 marble, or 2 white marbles. Multiply your branches out to find each of those probabilities. The middle one has 2 cases, so you'd have to add those 2 cases together. Again, we have a situation. So we set it up with a tree diagram. First, starting with Kirsty. She could get job or no job. And then Bridget. Job or no job, job or no job. These are interdependent events. Let X denote the number of successful applicants. So in your probability distribution chart, you could have no success. One of them got a job. Both of them got a job.